Let's do a quick overview of some ways you can solve linear systems. Some of my previous Calc 2 students asked me for this, partly because we were doing the partial fractions thing where we had to solve linear systems, and also because they were maybe in algebra, linear algebra, or they needed it for some other class, and hopefully we can make some connections between different topics too. So we had this linear systems to solve. So one way to do that is by substitution, where we solve one formula for b and then substitute that into the other formula. So we might say solve the second one for b. So sorry, the first one for b. So 5a plus 2b equals 63. Solve for b. So you subtract 5a from both sides, divide by 2, so you get b equals 1/2 63 minus 5a. And then substitute that into the other formula. So we have 7a plus 3 times, and then instead of b, write this thing. So 1/2 63 minus 5a equals 89. Solve for a. And I think you get a equals 11, and then plug the 11 back in this formula for b. (1/2 63 minus 5a), and get b equals 4. So that's the substitution method. Another way to do it is the adding equations together to cancel stuff method, whatever you want to call that. So you could multiply equation 1 by -7/5 and add to equation 2. So you'd have 7a plus -7/5 times 5a, that's from equation 1, plus 3b plus -7/5 times 2b equals 89, plus -7/5 times 63. And what happens here, the 5 cancels the 5, you get -7, so this whole term is just 0. So then you have some stuff times b equals some constant. Then solve for b, and then go and plug that back into a different formula for a. So we'd get b equals 4. Plug b equals 4 into, and at this point it doesn't matter which formula, but maybe we'll do equation 1. 5a plus 2b equals 63. And solve for a. So those are two very linear algebra ways to do stuff. You could rewrite it as a matrix problem. That's actually a good idea. You could rewrite it as 5, 2, 7, 3 times AB equals 63, 89. And then how are we going to solve that matrix problem? Some people like using a TI-83 kind of calculator, but I don't. You could use it if you want to. I'm not going to prohibit you, but it's not a very professional tool. Let's talk about some other ways to solve it. You can solve it in Excel using something called minv for matrix inverse, and mmult for matrix multiply. Let's show that. Here we are in Excel. I've got my matrix that I'm multiplying stuff by. I've got my right-hand side. I don't have a matrix of the A and the B, capital A, capital B. but I'll show you where that comes up in a sec. To compute the matrix inverse in Excel, by the way, Excel is not the best tool for this, but I just want to show all the different ways to do stuff. I want to get a 2 by 2 result from the matrix inverse here, so I'm going to highlight a 2 by 2 region, and then type equals minv for matrix inverse, m inverse, and then highlight this block, and then press close parenthesis, but I don't press enter. I hold down Control and Shift, and then press enter because I want this formula to get entered as an array formula in these in this 2 by 2 block. So there's my matrix inverse, and then if I do my matrix inverse times my b vector, that has to be a 2-row 1-column thing. So I highlight 2 rows and 1 column and type equals m mult, and then I want to do the matrix inverse, and then comma my b vector, close parenthesis, but again, don't press enter because that would just enter it in one cell. I want to enter it as an array formula, so I hold down Control and Shift and then press enter, and I get my 4 and 11. One nice thing about this is if you change one of these numbers, like 63, let's say that became 62, all the results end up changing, or if this 3 changes to a 4, everything gets recomputed automatically. Here I was just doing a 2 by 2 system, but if you had a 3-variable 3-equation system, Excel would work just as well. You just have a 3 by 3 matrix, a 3 by 1 vector, and you do that 3 by 3 and 3 by 1. That would all work fine. More professional than Excel, though, would be to use Python. So here's some quick code to do that. You have to use the NumPy library. You would define, here's my matrix, here's my right-hand side vector. We can ask it for the inverse of the matrix, and it gives that to us. And we can ask it to take the matrix inverse and multiply by the right-hand side. This @ sign is how you do matrix multiplication in Python, and it gives us our answer. A is 11, B is 4. I should mention, though, that while in linear algebra class we think of solving systems by doing a matrix inverse times a vector, in computer systems, if you're just doing it once, it's often better to call a specific linear algebra solving code, which actually doesn't need to take the whole matrix inverse. It's faster and a little bit more numerically stable, I think, and it gives us the same answer. So if you don't really need the matrix inverse, don't ask for it, just do a solver code. I should mention here that I'm using Google Colab or Colaboratory, which is a free online Python environment. It's really handy for quick stuff like this. Another way to solve the system is to tell Wolfram Alpha the system you want to solve. You can just write it in plain old linear equation form, and it tells you what it thinks you typed, which is good to check because it doesn't always get right what you thought you were telling it. And it tells us the solution, and it plots the solution set, which is an interesting idea that we'll come back to in a sec. So it's saying one of these equations is the purple line here and one is the blue line, and it even tells us which one is which, and where they intersect is the set of A value and B values that satisfy both equations. So that's kind of handy. We can actually go do that in Desmos. You can tell it, now here it has to have X's and Y's instead of capital A and capital B, but that's fine. It does the same thing, and if you want to know where those intersect, you can click on one of them and it'll show you the intersection with a gray dot, so we get our 11, 4. The downside to using Desmos here is if these things intersected at like 9, x equals 9 million, y equals negative 10 billion, you'd have to scroll out, zoom out until you found the intersection. So Wolfram Alpha kind of did that for us automatically. Desmos, you would have to go find it. Here's another interesting way to think of stuff in Desmos. You could think of it as a regression problem. You can do this in other packages too, where we have a column of one variable, a column of another variable, and our output results. And we're saying, give me A times this column plus B times this column to get as close as possible to this column. In this case, it can do it exactly because we have a 2 by 2 system and no invertibility problems. So it's really interesting to think, we can think of this solving a linear system as a multiple regression problem in statistics. Excel has a multiple regression tool. Python has multiple regression. Excel actually will refuse to do this because the matrix is square, which is interesting. It refused to do it as a statistics problem. It can do it with a matrix inverse problem though. All right, so that's our tour of solution methods. Some of them mathematical, some software-based. So we had Wolfram Alpha, and we had Desmos to graph and find the intersection. So a graphical approach, pure software. In some sense, we didn't have any idea what Wolfram Alpha was doing behind the scenes. Solving matrices, the combining equations method, and the substitution method. So that's a quick tour of a bunch of linear algebra, technology, and math. Aren't you glad you watched?